yeah, I had the interest from many years ago. So so in the 4 units, I will mainly report and explain the main results and the main method of what we have done. And so the first part, let me begin with reviewing on the results on the birational geometry of threefolds. On threefolds, mainly of general type. The problem probably it was starting with Myers, and actually it's stimulated by the interesting Riemann-Roch of Reed. And so let me state the problem. So if I take a smooth, say a smooth projective threefold of general type, we say it's a general type simply because when the integer m is large enough, so we have enough global sections of a pluricanonical map, then a pluricanonical system. So so that means this this group grows like something m group, and so it's interesting. So or it's equivalent to saying that the pluricanonical map is birational onto the image. Okay, so therefore it's very interesting to find some practical number, m, say the practical, so that phi m is birational. So this is a parallel to the classical story, by Bombieri and other algebraic surfacists. So so what we did is try to find some effective way to do this. So so yeah, of course. So we let me recall some birational invariants. For example, the first one is the canonical volume of this variety of this threefold V. So this is defined to be the limit of supreme of this maybe like this. Yes, and H naught of V M kV. Okay, you take M to be positive integers, and this is a birational invariant. And of course, some other birational invariants say plurigenous. So this is H naught of M kV. So here kV means a canonical divisor. And of course, the Euler characteristic, OV. So this is 1 minus irregularity plus H2 OV. And plus geometric genus. So all these are birational invariants, and parallel to surface theory due to Maurice Amino model program. So this successful MMP says that we can find the minimal model. Says this is a birational map. So yes. Sorry. Yes. Sorry. Plus H2 minus. Yes. Sorry. This is minus, of course. Thank you. And so we have a birational contraction map onto the minimal model. So this is a minimal. So in the threefold case, it is Q factorial terminal singularities. And everything can be done on X, since from the point of view of the birational geometry, the property of phi m is invariant and birational transform. So therefore, one can study on the minimal model. So it's this due to this the key point is we have the Riemann rock proved by Myers. So so if we want to study this the property of pluricanonical map, it's very important to to calculate the plurigenus. Suppose you have at least two independent linear sections then you can study the pluricanonical map. So therefore, the problem becomes how to compute this plurigenus. Okay, so let me recall the Riemann rock Riemann rock formula by Myers. So now from now on, I only study on the minimal model. As I said, it's the same thing to studying on the smooth model. So from now, so we have and due to the vanishing, it's so for Rm. So this is due to read for m larger than or equal to 2. So we have Pm of x. So this is 1/12 m minus 1 and 2m minus 1 kx cubed minus 2m minus 1 chi ox and plus the correction term due to the singularities. So so let's say this is some correction terms. So the observation is that Myers said that there is a basket of orbifold points on X, so that we can calculate this this plurigenus. So Myers said we can find a unique basket of orbifold points. Say this is one of type 1/Ri. So this is 1 minus 1. So this is terminal quotient singularities, Bi, and I from 1 to L. And here, so this is a orbifold terminal point. So this is Bi is positive. Of course, it's can be 2, and Bi is the coprime to Ri. Okay, so this doesn't mean that the minimal model has this type of singularity. It's something like virtual. It is just for calculate this the plurigenus. But if this minimal model happens to have or all the singularities are terminal orbifolds, then it's really exactly you calculate with this bx. And in this case, the bx appeared here exactly the terminal singularities on x. But anyway, so then LM should be calculated like, say, here, I from 1 to L. And then we can take J, Bi. So this means the smallest residue to Ri. I. And yes, from J from 1 to M minus 1. Okay. So anyway, we have this formula. So the difficult point is, for many years it's not easy to calculate this, especially when this threefold has some strange property. For example, when chi OV is positive, when this is positive, but the kx cubed is very small, then it's not easy to calculate this. And on the other hand, the difficulty happens on the number of singularity. Usually you don't have any control on the number of orbital points in the basket. Okay. So by the way, I forgot to say that. The smooth model of X, the volume is exactly because this is biration invariant. It's easy to prove that. So this volume is exactly kx cubed. So that means the volume on the minimal model. Okay. So if we can find some positive number m naught, so if m naught, so that p m naught is at least 2, then then it's convenient to consider the geometric property of this it's easy to study this phi m naught. And from this map, you can detect the birational property of pluricanonical map. Phi m for m very large. And this was clear due to the work of Janos Kolar many years ago. But anyway, this step is is effective. Yeah. So so the key point is to try to find some number m naught, and this is exactly what we did with several years ago. So this is a joint work with Meng Chen. From Taipei. Yeah, with Meng Chen we try to calculate this, but we didn't go do this directly. But the essential point is we rephrased Meyer's formula, and we did this in another way, and we use some combinatorial method. So let me just briefly explain, because this part is purely calculation, and it's independent of algebraic geometry. So, yeah, sorry. The bar, yeah, this is the smallest residue, module Ri, okay? Yeah, so we rephrase Meyer's formula. So it's easy to see that essentially you can say that the invariance, bidirectional invariance are determined by this triple. Let me say this is a weighted basket. So I only study on the minimal model. So anyway, this is bidirectional geometry. You choose one model. So let me define this weighted basket to be this symbol Bx. So this is a triple. The first one is a Reed's basket. And the second one is a P2 of X. P2 of X. And the last one is chi of OX. So all the invariants can be uniquely determined by this weighted basket. And what we did is, so we consider the set of, so X is a threefold of general type. Okay, and then we found some interesting partial ordering. Yeah. Ordering, yeah, partial ordering. Say with this symbol. This is what we mean. It's parking. This is parking. So yeah, excuse me that I don't define what is partial ordering here. So I just briefly recall this calculation. So I just mention this method. So on this set we have this ordering, and another point is so given a weighted basket, we can define some invariants. Say we define some invariants. Say the volume. The volume we define this by abuse of notation. We define several invariants of the basket. Say and so this is equivalent to volume. And another one is the plurigenus Bx. And for m equal to 2, okay. So of course, so when you this category can be slightly enlarged because yeah, this is formally defined. So we can work on a slightly larger category of the weighted basket, even if it is not corresponding to any threefold. Okay, but the point is that when this weighted basket really corresponding to some concrete minimal threefold of general type, then what we define here are exactly the same as the volume, the canonical volume, and the plurigenus of that threefold. Okay, so so everything can be done formally, and then after we found this, this partial ordering, we can prove that if the property is that if we have two formal baskets, say B1 is larger than B2, yeah, we can prove that our volume K cubed of B1 is larger than K cubed of B2. And on the other hand, for R, sorry, greater than. But this also includes the relation equality.
But on the right-hand side, it doesn't. On the right-hand side, there's just numbers.
Yes.
Rational numbers.
Rational number, of course. Yes. Yeah. This is, of course, it's right. Yeah. Positive rational.
The last one, K cube.
K cube.
Greater or equal, the usual greater or equal, not this curly one. In the K cube.
Lower.
Yes. Lower. Here. This.
Lower down.
Below.
Sorry, I don't understand.
The last formula there, K cube would be 1 greater or equal than back.
Here.
Yeah, you must use.
B2.
No. Greater or equal. Is the
Sorry. This is sorry. It's, no, this is yeah. No. This is sorry. Thank you. Yeah. Yeah. And on the other hand, we have the PM of B1 is greater than or equal to PM of B2. Okay. So so this is a very, very important property. So it's now the picture is like this. We have we have a set of baskets, say weighted basket. So so we want to find something. So for example, we want to find the lower bound, universal lower bound of the volume, and the universal lower bound of the plurigenus. So the point is that we found some partial ordering on this on this set. Okay, so maybe it's irregular, something, yeah. But finally we beginning from the left, you will finally find you get something on the right. So suppose you can find some effective bound on the right, or say on the minimal elements. You have control on the minimal elements. Then you get the universal lower bound, and the geometry is terminates on the right line. So so this can be combined with the argument originally started with Collat. So let me explain what we did. So starting with the Collat's program. So if you if there exists some integer m naught, so that p m naught of x is larger than or equal to 2, then you can study. Then I say it's okay. And otherwise, you should try to find this m naught. So our consideration is like this. So if we know that Pm of x is smaller than or equal to 1 for all m positive and smaller than 12. And this our consideration. Our method will say that So what we did is that the number of this satisfy this property. and X is minimal threefold. So the number of this set, this is actually a finite set. Then theoretically, it's yeah, one can do everything. So this is what we did. And another interesting point is that our calculation actually allows us to use many interesting inequalities between the invariants. So for example, let me mention several interesting inequalities here. So this consideration is, as I said, it's purely calculation without any geometry. Yeah, what we use, the only geometric property we use is, say, if you have PM, so this is positive. Then we use, then of course 2M, say Mn is positive, right? So this is what we use is very naive property of so essentially we don't you cannot say that this is a geometric consideration. So, but the disadvantage is that though we can solve this canonical boundedness, but another point is so from our calculation we will in our list we have come across many possibilities, but the possibilities like this weighted basket, it's not easy for us to determine whether this basket is really geometric or not. What I mean geometric, that means this really corresponding to some concrete threefold. Yeah. Otherwise, it's artificial, and we can throw away this. But this is a kind of geography. Yeah. Okay. So let me return to this finally. So here I would like to mention several interesting inequalities. For example, for all threefold of general type. So we have, for example, this inequality 2 chi of OX plus 2 P5. So this is P3 and P6. This is the first inequality. The second inequality is, for example, P4 plus P5 plus P6. So this is larger than 3, P2, P3 plus P7. And the third one is, so we have 2 P5 plus 3 P6 plus P8, P10, 12. So this is larger than chi of OX plus 10 P2 plus 4 P3, P7, P11, P13. So so in our paper we have numerous such kind of inequalities. So I said this all these inequalities are correct. So this why is correct? Because so one way it's our calculation. Also another point is it was first observed by Collat. He said that all these inequalities is easy to verify. Suppose you give me such kind of property. For example, this is all this can be verified by a single orbifold point. So it's something like you just verify. You input any basket, any orbifold terminal point. And then you verify this with this singularity. Yeah. So this actually this was done in another work by Meng Chen and Haken. So they have a note verify this from the point of view of the really calculation on the terminal orbifolds. So we have all these inequalities. So the third inequality is interesting. For example, how can you recognize this point? For example, if you assume that all PM for m smaller than or equal to 12, all these are smaller than or equal to 1, then on the left-hand side, you say this is 1, 1, 1, 1. The left side is bounded. And then this means that the chi OX is bounded, and plus some other properties. So this already says that the triple, you can see that the triple is bounded. And then in our paper, we have with Ron Kai we have three papers. So say explicit Barrett geometry of the 1, 2, and part 3. The first two are published, and in the first two parts, we try to give a raw list to this case. So originally we have the third paper. So from now on, I mainly talk about the up-to-date results and methods. So we can give our results in a much better way, and all the results are updated, and we found some interesting application on fourfolds. But in this series of lectures, I will not refer to. I have no time to refer to fourfolds. And so the part 1 and 2 implies that this m naught is not too big. So the main result is that so our result is that there exists m naught smaller than 18, so that Pm naught is larger than or equal to 2. And then the next step is beginning with this property. We will optimize the argument of Collat. We will excavate Collat's method and try to improve his technique and to study the Barrett geometry of threefold generator very explicitly. So I want to start with from this point. So excuse me, I don't recall other details because, for example, in the first part, it's really calculation. And I believe that the calculation is correct. So so from now on, let me begin with the following definition. So given a threefold general type, say X, I will define the pluricanonical index section second index, the pluricanonical section index. Say delta of X. So this means the smallest number. Smallest number m, so that the Pm of x is larger than or equal to 2. So, so from our previous work, we say that this index, let's say PS index. Okay, the PS index delta x is, of course, this is positive, and on the other hand, it's not exceed 18. So essentially, we can classify threefold of general type into these 18 classes. If you can treat every cases very explicitly, then you have a very global, very general picture on birational geometry of threefold of general type. So so let me first state our up-to-date theorems, and then I try to explain how to prove our result. So I would like to introduce the following theorems. So all these are all these are included in part 3. So the first theorem is Since all these are joint, my joint work with Meng Chen. Yeah. So the first theorem is forgive me that I only introduce this very briefly. So I don't write all the details on the blackboard. So say V is a threefold of general type. So V is always assumed to be non-singular projective, threefold of general type. I say that this is of course the PS index is birational invariant, of course, and then the first statement is like phi of M is birational onto the image for R M larger than equal to 61. The second statement is that the canonical volume of any threefold of general type is larger than equal to 1 over 1618. So the inequality holds. If and only if the weighted basket is this type is B 7A 02 R B 36A 02. So what is B7A? So these are listed in our papers. Forgive me, I don't write this here if I don't refer to more details. So anyway, it's we can recognize this, and this is this corresponding to spatial types of readers basket. It's a combination of terminal orbiform points. First, sorry, we don't know. We are not sure. I mean, we don't know whether this is optimal. Yeah.
Sorry.
Yeah.
You should use German system. So you wet this water
Ah, sorry. Yeah, I should use this. Yeah, forgot. Yeah, forgot. Yes, yes.
Then you
Yes,
like
yes.
for that and dry.
Yes. Yes, I forgot. Yeah.
Not so much. This is much better. If you know how. If you know how to do it, it's much better. Dry.
I think you're missing the point. Here, assistant.
So where is right? Yes. Ah, sorry. Let me do. It's okay. Yes. Yes. But in viroid, it's separated. Okay. Okay, thanks. And so this is a first statement. Here we don't know. Whether either of this is optimal. But this second, for example, the second one is only theoretical. We don't know whether this equality really holds. So the second one. So we want to disprove this. We want to prove that this doesn't exist. That means you have to use geometric property to prove that this doesn't exist. But this is not so easy. So but in our previous papers, we now this statement is much better than before. But still, it's incomplete. So this is the first.
The real issue there.
Yeah. Yes.
Equals 2.
Yes.
And that means that H naught of omega 2.
Yes.
The variety has Hodge number. H20
Yeah.
equal 1. And we don't
Yes.
have any example of that.
Yes. Yes. Yeah. So far, it's we have But by the way, the famous example, by my student, it's by Fletcher. It's the volume is 1/420. I remind this in each lecture. But here it's slightly smaller. But it's very interesting to find examples of minimal threefolds of general type with very small volume. So this is an open problem. So the second theorem is that. So if we assume the pluricanonical section index is larger than 13, then it's possible to list all the properties. So then we have a very complete description. But this is also theoretical. Not For example, the PS index equals to 18 if and only if the weighted basket is of this type, the 2A 0 2. So the last one is chi. This is chi of OV. This is P2. Okay. So the first one is a special type of Reed's basket. So this is the first. And how about 16 and 17? So if the PS index cannot be 16 and 17. And the third one is the delta of V equals to 15 if and only if the weighted basket is in the list of table F1. F mean our final one. But this table contains 8 cases. So if you want to take a look to what the table look like, you can check check our paper 3. This is in archive. Okay, the fourth. So this is the most broken case. So this delta V equals 14 if and only if. So BV is in table final 2. So this is a very large table. It's 100. It's 78 cases. And finally, so delta V equals to 13 if and only if the weighted basket is, so this is B41 and 0, 2. Okay, this is so far what we can understand. And so you will ask me what happens to delta V smaller. Okay, so I only have a remark here. So if delta V smaller than 12, you cannot prove that. I believe that it's not. So say even if it's 12, this is not finite. This is infinite. I'll say this. I mean the set of the basket. 12. I should say this is J for here J. So this is not finite set. Yes. So it's not easy. No, it's not hard to prove this. But I would rather put this as a remark. So it's impossible to list. It's infinite set. Okay. So
the geometric ones are finite set. No.
What do you mean geometric one?
Coming from threefolds, really.
Yes.
They are finite one or no?
Yeah. 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 No. This delta V means the smallest number. So yeah. So delta equals to 1 means PG geometric genus equals to 2. Yeah. Yeah. So of course this is an infinite class. Yeah. So on the other hand, we know the case when delta V is So when recall. Let me recall this. So when delta of V equals to 1, so my earlier papers tells me that. Then we know that the volume of V is at least 1/3. And on the other hand, we know that the phi m is birational. For R m larger or equal to 8. So both these are optimal. Okay. So apart from this, we don't know any other results. For example, what happens when delta V is is bigger than 1, is larger than 1, and but smaller or equal to 12. So yeah, so when delta v is larger than 13, we have a complete list. So what happens to to the middle case? So we yes. Yeah. No examples correspond to any cases here. Sorry, yeah. This is only theoretical. Yeah. We don't have examples. Yeah. Yeah. The champion example has got delta v equals to 10. This is Fletcher's example. Yeah. For others, we don't know any examples larger than 10. So so now let me write down the third result. If our result is like this. So if delta v equals to 2, then what we know is that phi m is birational for m larger than or equal to 11. So we have now this is optimal. We have 3 examples. 3 supporting examples. So even in the case of PS index 2, we don't know the really lower bound of volume. So our conjecture is there is conjecture. The conjecture is the volume of volume of V 12. But so far we couldn't prove this. But a couple of years ago we announced this, but finally we found some gap. We cannot prove. This is only for delta v equals 2 case. Okay, so in general. So in general, we have a function for the lower bound of the volume. So for example, for 2 delta v smaller than 12, we have the volume larger than or equal to some function in terms of delta v. So this function, what is this function? So we have a table here. So x, so here is vx. Okay. So if this is 2, what we can prove is this is 1 over 14. If 3 is 1 over 36, and this is 4, we have 90. And 5, 1 over 5, 6, 1 over 2, 2, 4. And 7, 1 of 3, 6, 8, 1 of. And the last one is 1 over 1560. So, sorry? X, this is a function. This is a table function of V, Vx. X should mean this delta V, yes. Yeah. Sorry. Okay, so so this is something like geographical problem. yeah, we have we have much work to do. So we have to find examples. Yeah. So unfortunately, so far we have no idea. So, so one possible way is, you can use geometrical properties of threefolds to prove some effective inequalities. So we have a large table. So if what you get, I mean, if you can deduce some lower bound of the volume, which is larger, strictly larger than these ones on the table, then that means this basket does not exist, or it's not geometric. So this is the only strategy we can do. So this is something like so you want to find a lower bound. That means you should have some inequality of Noether type. Like on the surface of general type, you have k square larger than equal to 2pg minus 4. Some effective inequalities of Noether type. So this will be third topic. But now I want to to start with part 2. So the problem is like this: you given a threefold, a minimal threefold x of general type, and I assume that m not so that and the p of m naught is larger than or equal to 2, then how can we recognize the birational geometry of this kind of threefold? So usually we will do like this. So we can find some sublinear system. For example, we can find some any sublinear system, take any sublinear system lambda on this complete linear system kx. So this linear system is extended notion because x is not smooth, but it's well defined. So we have we can find any sublinear system lambda here, and then begin with this. We want to deduce the inequality for the volume and the birationality. So so we can do it in this way. First we have x here. So then we have a sublinear system which is moving. So we have a rational map defined by this phi lambda, and so this is in some projective space. So this is a rational map corresponding to linear system, and then we take the birational modification to get a smooth model x prime, so that the composition is a morphism. And then we take the Stein factorization to get induced vibration gamma, say. So this is a finite map S. So this is a vibration F. So usually we will get the induced vibration. So say F x prime to gamma. Okay, So so upstairs on x prime, so we do everything on the smooth model x prime. So so let me write the m lambda to be the moving part. The moving part of the linear system of the pi up star lambda. Moving part of this, but this is not complete, but the moving part is complete. Okay, so let me write this. Yeah. Okay, and of course, then you get m lambda. This is this is smaller than the m naught of kx prime. Okay, so mostly we will take this lambda to be complete, but in some cases we will just take lambda to be some tensor. But anyway, this is something generalized. But we can we take some after blow up the general member in this base point free linear system should be smooth. So I take so there are two cases. So first, if dimension of gamma is larger than 1, greater than 1, and then the general member S in this linear system is so this is irreducible and non-singular. Okay, so this is due to Bertini's theorem. And on the other hand, if dimension is 1, I mean the dimension of gamma is 1, or gamma is a curve and x prime is threefold, then this is induced vibration. So the general fiber is a smooth surface of general type. And but the general member of this is can be a disjoint union of several smooth fibers of F. Okay, so then I say that m lambda is equivalent to a disjoint union of say I would like to write in the vibration case I would like Fi. So the sum of disjoint smooth fibers of F, where each Fi is a smooth surface of general type. So this is numerically equivalent to number T of F. So here F is a general fiber of F. Sorry. So starting with this, we will study the geometry and the volume, how to start the volume, and how can we prove the birationality. So I would like to talk about this tomorrow. Okay? Thank you very much. Yeah.
Thank you very much. Are there any questions, comments, remarks?
If you fix one of these basket types,
Yes.
do you expect there is a finite type moduli space for threefolds?
Yeah, this is there are problems. First, we don't know the existence. Mostly in our list, we don't know whether those exist. So it's yeah, we didn't really consider moduli and deformation of this. Yeah, because we don't know the existence. I don't know. Yeah.
So it would still be possible to have 5n birational,
Mm-hmm.
but nevertheless the singularities of the map
Mm-hmm.
being worse and worse in different components.
Mm.
It's probably true. It's in your sort of implicit conjecture. It's probably true.
Mm.
It's probably quite a long way to be improved.
Mm-hmm.
So, I have a general comment.
Yes.
You're only using,
Yeah.
you're only using one set of invariants. So
Yes. Yes.
invariants are plurican.
Yes.
The things coming from coherent cohomity. So, there might be other methods
Mm-hmm.
coming from topology or coming from Hodge theory or something that, are just completely bypassing it.
Yes. Maybe. Yeah.
So, for example,
Mm.
the surfaces of general type,
Mm.
if you have if the canonical class is divisible,
Mm.
then you can apply Serre duality to the submultiple for the canonical class. And sometimes you get statements that some cohomology group is even dimensional.
Ah.
Just because this is symmetric.
Yes.
Parent.
Yeah.
And, for example, your